Good afternoon, ladies and gentlemen. This is the concluding part of the topic we have introduced before on being solutions and solubility. It's going to be Latif. Before we have explained what is meant by solution, when we said it's a combination of majorly two things. The first one has to be the solute, then the second one has to be the solvent, where we said the solvent is the dissolving substance. Any substance that dissolves another one is a solvent, where the solute is the substance being dissolved. So we went ahead to explain that in some cases when we have almost 100% miscibility, as in the case of ethanol and water, any water that is present in higher amount is called the solvent. It is not necessarily that water is the solvent for ethanol. Sometimes ethanol can be the solvent of water, depending on which one is more than the other in that mixture. More than the other can be maybe in terms of mass, in terms of volume, or in terms of mole. So any quantity, any way that another one can be more than the other is what we refer to as more, as in higher than the other, maybe in terms of concentration, something like that. So we still define saturation in terms of concentration. So we went ahead to explain what we mean by the unsaturated solution, saturated solution, and supersaturated solution. I hope we have understood that. So today we are going to another concept, although not different concept, but it's just the conclusion to what we have discussed before. Having know what the solvent is, having know how to make a solution. Now we want to know much more about solvent. What are the things that make this solvent to be able to dissolve the solute? If we take one solvent as an example now, let's say water now. Why is it that water cannot dissolve palm oil? Water cannot dissolve vegetable oil? So that is what we want to discuss today. And again, if we have a mixture, what are the possible outcomes as a solution? What are the possible outcomes, the structure of the product that we can get when we have two things mixing together? So that is what we want to discuss today. So after today's class, it is our hope that we will understand the principle behind solvent selection, how to select solvent based on some criteria, then again how to describe between solution types and give some examples of the solution types. So what is called a solvent? As we have said, solvents are the substances that are used to dissolve another substance in contact with it. So if we have water and let's say ethanol, assume that water present in larger quantity than ethanol. So water serves as a solvent for ethanol simply because ethanol can dissolve in water. So ethanol is now a solute. So this particular solvent principle is used in industry and homes, especially in chemical industry and petrochemical industries. So even in paint industry, they deal with solvent to a very large extent. Even in our homes, we deal with solvent and how to remove stain from maybe our clothes, or even if we heat, washing our plate with soap, with detergent, is application of solvent, because if we heat in a particular plate now, we cannot use only water to wash our plate. Instead, we employ the use of detergent, wash, some other type of washes we can use, and this is based on the ability to dissolve another substance. That is the principle that solvent selection is based on if we want to use it, because we can't say we want to produce a solution where the solvent will not be soluble, where the solute will not be soluble in a solvent, so that one is not a solution. To form a solution, we actually need solute to be soluble in solvent. An example of solvent in industries can be hydrogen peroxide. This is want to remove paint. I want to remove stains. Sometimes in industry they use methanol, they use acetones, they use ethanol. There are many solvents to use, but the principle is that like dissolves like. What we are saying is this: water is able to dissolve ethanol or methanol or propanol, even butanol. It is simply because they are like the chemical bond in them, the structure in them, they are very similar to each other in a way that they have hydrogen bonding in them, and hydrogen bonding make them very soluble in water. That is why they can act as water can act as solvent for them. In a case when we have organic material substance like palm oil, like other oil, water cannot be used simply because water is inorganic and contains hydrogen bond. So any other materials or substance that is inorganic and that is organic will be used to dissolve organic substance. So that is another principle: like dissolves like dissolve like material. So polar dissolves polar, non-polar dissolves non-polar. So we cannot use a polar material substance to dissolve a non-polar substance. It will not work. It is only when we have a polar substance that we use it to dissolve another polar substance. Polar substance, we have explained that during chemical combination, when we have a partial positive and partial negative in the bonds that connect them together. So if you have that in solvent, we have that in the solute, then the positive will attract the negative in the solvent solute, then the other one will attract each other. So they were able to exchange the polarity, then dissolve in one another. So but in a case where one ionizes like that, such that it forms positive and negative, although partial, the other one does not form, so there's no way they can be able to dissolve in each other. That is why polar and polar another substance that is polar, they are able to dissolve one another. So if we have another substance that is not polar, we cannot select a polar solvent for that. That is that on solvent selection. And having known what is called a solvent and solute and the way they can react to form a solution, so there are some types of solution that we have seen or maybe we have not noticed. There are many possibilities that can be formed apart from the color. I mean the structure, how the solution should look like. So, for example, now if we have our table salt, we put it in water, it is not the same way the solution will look when we have chalk dissolved in water. Apart from the color, I mean the particular makeup, the particles inside the solution. It is not the same way if we produce a starch. So those are solutions, but different look, different structures. So it is on that note that we need to explain each of them and give possibly some examples of each of them. So the first one is true solution. True solution is just a homogeneous mixture, as we have said. That is for solution. Solution must be homogeneously mixed. Homogeneous mixture means anywhere you take a sample, it is going to be a representative fraction of the other. The composition does not change with the side with the portions of the solution. True solution is a homogeneous mixture when we have this the particle of that solute less than 1 nanometer. They're very small. It is like we are dissolving sugar in water, we are dissolving salt in water. Simply because this particle is very small, like less than 1 nanometer, if you want to separate them, we cannot use filter paper to separate them, because the particles are very small. They will pass through filter paper. All of them will pass through the filter paper. Filter paper will not be enough to hold them, because the holes in the filter paper are even larger than 1 nanometer. Of course, the molecules are very small. They are not visible to our naked eye. Even to microscope, they are not visible to that, unless if we have a ultra very high power microscope, which I can see. Another one is the suspension. Suspension is what we have been seeing. We have a solute, we have a solvent. They dissolve in each other, but the particles are still very, very big. They are very, very big. The example is when we have a mud dissolved in water. Initially, we are going to when we study it vigorously, we are going to have homogeneous distribution, but later, even without centrifuging, when we just leave it like that, the weight of the particle, because the particles are very big, the weight of the particles are large enough to cause them to settle at the bottom of the container. That is just due to gravity. They will settle down, and we have a class separation of the solute and the solvent on top. That is an example of a suspension. Particles of suspension are big enough to be seen with our naked eye. That is when they are able to settle. If they are not big enough, they will not be able to settle down under gravity. Another one is the colloid. Colloidal solution is just in between true solution and suspension. The particles, in terms of particle size, the particle lies between the size of this true solution and the size of the suspension. So the example of this one is the smoke from fire. So when we have the smoke, although we cannot hold it, that is why this that is because the size is very small. We have a smoke dispersed in air. So that is an example of colloidal solution. So when we have a thick smoke, there are times that those in the village, you see some cars, when they are going like that, you see smoke following them. Very thick smoke. So example of that is what the colloidal solution is. At that particular place where they are thick, it will be looking as if the eyes is seeing the molecules, but the eyes are not. The eyes are not actually seeing them, but the conglomerate of them, that is what the eyes is seeing. But individual molecules are very small, eyes cannot see them. So this is in tabular form that represent the summary of what we have been discussing. In terms of the size of molecules, the true solution is the smallest one, the suspension is the biggest one, it's greater than 1000 nanometers. So the colloidal solution is in between them. So in terms of the nature, the structure of the solution, the solution is homogeneous because it is complete dissolution in the solvent. Others are heterogeneous because the heterogeneous, that is where we are able to see the particles. Had they mean they are homogeneous, they will have been part of that solvent. So we're not seeing anything apart from if they are color. That's when we'll be seeing color. But to be seeing molecules, it means they are heterogeneous. So because the particles of true solutions are very small, they can diffuse through filter paper and parchment paper because they are very small. The holes in these papers are bigger than them. They can pass through them anytime. But in suspension, the particles are big. you can pass through any of the papers. See, parchment paper or filter paper. I believe we all know what is called the parchment paper and filter paper. So I want to assume we know it, because we have talked more about those two papers during like first 3 lectures. Yeah. So colloidal particles, because they are in between the two of them, so they can pass through one and leave, they cannot pass through the other. So the parchment paper is the holes in parchment paper are very small compared to what we have in filter paper, so they can pass through filter paper. The other way around, they can pass through filter paper, they cannot pass through parchment. Yeah, I'm correct, they cannot pass through parchment paper, because the parchment paper is very small. The holes are very small compared to what we have in filter paper. So in terms of visibility, you can see the particles in true solutions because they are very small. In suspension, we can see them. In colloidal, yeah, we can see them, but that will be aided and not by our naked eye. That is when I explain the example of a smoke suspension, the smoke particle suspension in air. The smoke in conglomeration, we can see them, but each individual, if you want to be seeing them, that means we have to analyze them using high power lens, not just ordinary eye. Tinder effect. What is called Tinder effect is just the ability of material to scatter a ray of light coming. If we have a ray of light coming straight like this, on getting to the molecules will scatter it. It will be going like it is. The rays are tapered. That's what's called Tinder effect. So because the true solutions are homogeneous, they are very small. In fact, it will be like there is no particle inside. So it does not show any Tinder effect. The light will just enter them and pass. Colloidal can show it because it has comparatively bigger particles as compared to true solution. Show Tinder effect. But in suspension, they might show it or might not show it depending on the time that this particular light is passed through them. So if it's immediately after mixing, so it will show Tinder effect because the molecules are still randomly moving in the solution. But if it has been left for some time such that the big particles have settled down, that means the hot particle will pass. We allow the light to pass, not Tinder effect. Then the down particle will not even allow it to pass, not Tinder effect also. So it depends on time and the size of the molecule that will determine if it's going to allow Tinder effect or not. Of course, transparent is the solution. Then colloidal solution is translucent. Translucent means something like it is not transparent. You can see through them but not clearly. That is translucency. Then opaque. So in terms of the weight of the particles, of course, true solution is the lightest, followed by colloidal solution, then suspension. If we have the same quantity of them, but because the particles are biggest in suspension, the weights are the largest among the three. So true solutions are small, and the particle cannot be seen with naked eyes. So false solution has larger particles and that are very large enough to be seen with our naked eye. Then again, we have said true solution can pass through filter paper, false solution cannot pass. Then what is called dialysis, that is a medical science when they prepare solution of higher concentration and solution of they put a particular organ inside, then there's going to be movement from higher concentration to a region of lower concentration through a semi-permeable membrane. That is what is called dialysis, like osmosis. So it is we can dialyze, we can use in dialysis true solution because the particles have dissolved completely in the liquid, so they can pass, all of them can pass through that membrane into the other side of the mixture. But in first solution, they cannot pass because the particles are big. In fact, the particles are bigger than the holes in the membrane, so they cannot be dialyzed. So true solution do not scatter risk. That is what is called tender effect. For solution does. So if we look at all this comparison now, I think we can see that true solution, example for true solution, but false solution, they are more of suspension, as we have said. So let us try to get some review of what we have done. Water is used as solvent for many substances due to its power of dissolving. It can dissolve many substances, and again, apart from water, we can have some other common solvents. Then solute and solvent must be alive for the solution to take place. That is what we call like dissolved like. And the particles of solution are not seen with our naked eye. That is just a small review of what we have discussed today. So these are the exercises. Liquid that will dissolve fat is dash. Fat is an organic substance. It's not polar. So every other thing here, you have to look at the polarity. Are they polar? Sodium hydrochloric acid, yeah, it's polar. What about calcium hydroxide? What about water? What about kerosene? The only one that is not polar here is kerosene. That is why kerosene will be our answer. Non-polar solvent versus non-polar solute. The solubility in mole per dm cube of 20 grams of copper sulfate dissolved in 100 grams of water is thus. Our solubility is the amount of substance dissolved in 100 ml or 100 grams of water. So now the question is now asking us to convert into 1000. How many grams of copper sulfate can be dissolved in 1000 grams or 1000 cm cube? That is 1 dm cube of water at 180. Just a matter of converting that. If 200 can occupy, 20 grams, that means 1000 grams can occupy like 10 times of that is 20. That is 200 grams. So we look for the molar mass of copper, the sulfur and oxygen. If you do that, you're going to get 159. So dividing 159 by dividing 200 by 159, we are going to get 1.25, and this is the solution. Just look at it and compare your answer with this one. Saturated solution is said to contain that. This is just a simple definition of saturated solution that we have discussed before. It contains more solute than it can actually dissolve in presence of undissolved solute. That is option A. So 117 grams of sodium chloride was dissolved in 1 dm cube of distilled water at 25. Determine solubility in mole per dm cube of solution at that temperature. 117 in 1 dm cube. So it is simple. Just convert 117 grams into mole. How many mole can we get in 117? So what is our compound? Our compound is sodium chloride. Sodium chloride, we have to find the molecular mass. Then from our mole that we have discussed before, the concept of mole, that is in stoichiometry. So mole is mass of a molar mass. The molar mass of sodium is around 50. That is sodium 23 plus 35.5. That is 58.5. 58.5 to 117 divided by that, we are going to get 2. That is option B. They are simple as that. So calculations on that solubility are very, very simple. The solubility of different solutes in a given solvent can be compared. So even apart from solubility, if you want to compare two things, you have to compare them on the same platform using the same quality. You cannot just set a scale for one, set a different scale for the other. So if you want to compare solubility, you have to plot the solubility curve on the same axis, both on the y-axis, the same y-axis, and the same x-axis. That's why you're seeing axis in plural letter, in plural form like this, axis. So the y the same, x the same. So then the values are plotted on it. That is, if the values are plotted like this, you are going to see different. Oh, this one is soluble more than this at different temperatures. Option B is the answer. The solvent used for removing grease stain is thus. In fact, this is one of our examples when we are discussing solvents in page 1 of this lecture. So ammonia solution is the answer. Stain, grease. Ammonia solution is the answer. Turpentine is used to dissolve oil. Ethanol is more of polar solute. The ammonia is closer to grease stain than every other ones. That's option D. Solubility of salt of molar mass 101 at 20 is 0.34. If 3.4 gram of that is completely dissolved in 250 cm in a beaker, the resulting solution is that. This one is a bit more involved, but it's not difficult. We have a particular solution, a particular salt of 101 gram, that is the molar mass. We don't want to know the salt, but it can dissolve 0.3 mole in 1 dm cube. So that same salt, if 3.4 gram is now put in 250, is the new solution now. What is the fate of it? Is it unsaturated, supersaturated, or saturated? That is what the question is trying to ask us. Again, we have 0.34, so let us leave that one. Saying we are going to convert 3.4 grams now in 250 cm cube to a number in mole per dm cube. So any one that is bigger, is it this one or this one? We now determine what is our resulting solution. So 1 ml of that water contains this. 1 ml contains 100 ml contains 0.034. That is what we are saying. Then what is the mass? 3.408. So for the second solution, 250 ml contains 3.40. So 100 ml will now contain how many? That is because we are using 100 ml as our scale here now. So 100 ml will now contain 1.36. So comparing 1.36 and 3.4, we are seeing that this new solution is actually far less than the whole solution, so it's unsaturated. Another way of doing it is the first one I've explained, is just to leave this one, then to convert this to a number in mole per dm cube. So if we convert that to a number in mole per dm cube, we have the molecular mass already. This is 3.4 grams in 250. So in 1000 cm cube is going to be 4-fold of that. 3.4 multiplied by 4, that is 13.6 grams in 1000 cm cube, that is in 1 dm cube. So 13.6 grams is now the mass that contains in 1 dm cube. So we now convert that 13.6 grams into into mole by using 1.01 grams. So if we do that, we are going to get 0.134. Although I did not work that one here, I just leave that one for you to solve on yourself, but I will just explain it. So 0.134 mole is the value. We are seeing that it's far less than 0.34 moles per dm cube. So any way that we do it, we are going to get the same answer since it is calculation. So far you are doing what is correct. I hope it is clear. So let us now have one piece of homework to just let our knowledge. 24.4 grams of lead nitrate were dissolved in 42 grams of distilled water at 20. Calculate the solubility of the solute in gram per dm cube. This water, it make it simple. 42 grams is equal to 42 ml. So if you have 24.4 grams in 42 ml, then how many will you have in 1000 ml? Just then do the calculation and you're going to get 501. Although it's 580.9 grams in 1 dm cube, so it's approximately 501. That is option C. I hope you enjoyed the class. If that is the case, let us meet again on acid, base, and salt. So thank you very much for listening. God bless you really good. See you later.